we are going to be having Hsieh, who is going to be talking about the Themis asteroid family, a potential source of ice-rich near-Earth asteroids.
Okay, so so thanks. So yeah, my name is Hsieh, and I'm happy to be able to talk to you all today. So thanks to the organizers for the opportunity. So today I'm going to be talking about the Themis asteroid family, a potential source of ice-rich near-Earth asteroids, and this is work I've done with my collaborators, Norbert Schoghofer, Kevin Walsh, and Boyan Novakovic. So, so I know I'm the last speaker in the session, and we've had a long morning or afternoon. So I thought, just to make sure I get my message out, I thought I'd actually start with my conclusions. And this will also help guide everyone else to kind of see where I'm going as I give this talk. So basically in this work, we did dynamical integrations that indicate that dynamical pathways exist from the Themis asteroid family, which is in the main asteroid belt, to near-Earth Jupiter family comet-like orbits. So these are have tisserand parameters of less than 3 and perihelion distances of less than 1.3 AU. We then did thermal modeling of these objects as they evolved from the main belt to near-Earth space. And then we found that if they had ice to begin with, that this ice could actually be preserved fairly near the surface, like within 5 meters or so, in the polar regions if the object tilts are not too large. And so based on those results, we suggest or conclude that if some Themis family asteroids are icy, as appears to be the case, some currently observed active comets could actually originate from the main asteroid belt. So that's, we find really interesting from a scientific perspective. And then also that other inactive near-Earth asteroids with accessible ice could be identified by their dynamical and rotational properties. So that's so for the exploration oriented people here. And this is funded by NASA Solar System Workings and the survey programs. So, so Marco actually did a great job of introducing families, which is great, which means I don't have to talk about them. But I will focus on the Themis asteroid family itself. So it is one of the largest and oldest asteroid families in the asteroid belt. It's thought to have formed about 2.5 billion years ago, and about 5,000 members are currently known. And its largest member, which gives the family its name, is the asteroid 24 Themis. In terms of composition, the family is dominated by objects with primitive type spectra, so C-type or B-type. And this is consistent with its location in the outer main asteroid belt at about 3.1 to 3.2 AU, as you can see from the semi-major axis versus eccentricity plot there. Very interestingly, there seems to be evidence that there's ice, present-day ice in the Themis family. First, there are these objects known as main belt comets, which are objects that orbit in the main asteroid belt, but they have exhibited comet-like behavior sometime in the past and at the present time as well. And basically, this cometary activity implies that they have present-day surface or near surface ice. And actually multiple MBCs are actually known to exist in the Themis family. Meanwhile, there's actually also independent spectroscopic evidence of ice in the Themis family in particular. People have looked at large Themis family asteroids because these are easier to observe, and they've actually found absorption features that correspond to water, ice, frost on a couple of these asteroids. And so you see the spectrum of 24 Themis itself there. And so what we want to know is what happens to icy Themis family asteroids that escape the family, if they indeed escape. So that brings us to the first component of our work, dynamical analysis. So basically, we're trying to see what happens to Themis family asteroids over time. So what we did is we created test particles representing all of the known Themis family asteroids, and then we integrated them forward in time for 100 million years using the Mercury 6 hybrid integrator. And then we took the output, which was, we had several time steps, and classified the intermediate orbital elements as these objects evolved into different dynamical categories. So here are the results. You don't really have to look into the table too much, but basically the punchline is that the vast majority of our test particles remain stable. They remained in the Themis family, or at least in the main belt, for the entire duration of our integrations. But about 1% did escape from the main asteroid belt. So this is an example, or these are some plots of one of the objects that did escape. So on the left there, we have semi-major axis versus eccentricity and semi-major axis versus inclination plots. And so you can see the sort of the big black dot is where this particular object started within the Themis family, which is the kind of massive small gray dots. And what happens is that it's sort of on the outer edge of the family, which is close to the 2-to-1 mean motion resonance with Jupiter, which tends to destabilize small bodies. And so the object basically encounters the resonance, and then once it does, it has its eccentricity and inclination pumped up, basically. And when the eccentricity reaches a certain point, as you can see in that top left plot, it can actually cross this perihelion of 1.3 AU line, which actually makes it a near-Earth asteroid. On the right, you see sort of orbital elements versus time, and you can see that the transition to, so the blue dots basically show when it's in the Themis family or the main asteroid belt, and the red dots are when it becomes, basically it has a dynamical characteristics of a Jupiter family comet. And you can see the transition to the cometary orbit is accompanied by many close planetary encounters with Jupiter and Mars, basically, and that's that bottom panel down there with the colored dots. So, so what we conclude from this is that for objects that undergo this evolution, it's driven by eccentricity excitation by Jupiter, which then causes the object's orbits to start crossing orbits of other planets. And during close planetary encounters, the Tisserand parameter gets lowered to cometary values. And what's interesting is that this does not appear to be uncommon. Like I said, it's about at the 1% level, which is actually, pretty substantial. These objects appear to have very similar properties to other comets, except that their semi-major axes are clustered near the original position of the Themis family, so 3 to 3.5 AU. We think that the implied contribution to the comet population is fairly modest, on the order of a few, but we did make some assumptions, which means that this could actually be, we made some assumptions in the modeling, which means that this could actually be quite a bit higher. So, so that deals with the dynamics, but we want to know what happens to the ice itself. So, so then we did thermal modeling using the dynamical. Sorry.
You're 8 minutes, by the way.
Okay, thanks. So then we did thermal modeling using the dynamical trajectories of these objects as they traveled from the main belt to near Earth space. This thermal model uses sort of a combination of two models. It uses asynchronous coupling between a 1D thermal modeling that uses small time steps to capture subsurface conduction, and ice evolution model that kind of captures a larger scale evolution that takes into account the changing orbital properties as objects evolve dynamically. And then we recorded the temperatures and depths of ice over the course of each object's history, and track them as a function of time, latitude, and axis tilt and thermal inertia. So this is the results from the same object I just showed you earlier. Basically these are the plots to focus on are the second and third ones, where the blue plot is the temperature at the poles of an object with an axis tilt of 25 degrees from vertical. And the red plot shows a more extreme axis tilt of 80 degrees. And basically what we see is the temperature at the poles remains quite a bit colder than the object with the higher axis tilt. And if you look at the bottom panel, which shows the depth to ice, you can see that after some initial ice loss, the depth to ice for the object with modest axis tilt actually remains fairly constant over very long time scales. Especially compared
10
to.
minutes.
Okay, thanks. Especially compared to the one with larger axis tilt. So we also just took a histogram of all the objects that we integrated and found that all objects, if we assume with all these different trajectories, we assume it has a modest axis tilt, they have depths to ice of 5 meters or less, which is really exciting and interesting. So what we found in terms of our key, the key takeaways are that ice loss is actually dominated by the time spent in the asteroid belt because the time scales are so much longer than the time spent as an NEA. And like I just said, objects with axis tilts of 25 degrees can actually retain water ice near the poles within a 1 thermal skin depth beneath their surface. And this is, we think, pretty exciting because it means we could potentially identify near-Earth objects with shallow polar ice by identifying objects with semi-major axes in the outer main belt and have small axis tilts. But this is pending studies studying how axis tilt might evolve over time, which we didn't consider. And with that, I'll just put up my conclusions, which I already explained to you. And you can see the 2 papers there if you want to get more information on our project. So with that, I'll end. Thank you for your time, and I'll take any questions. Thanks.
All right, thank you, Henry. It looks like we are almost out of time, but if you have a quick question, like a really quick question that you want to ask, we are heading into the discussion time, and this would be a good time to continue with this discussion and ask any further questions.
This is Marco Delbo. I have a question for Henry, if I can.
Yes, go ahead.
Sorry, I can raise my hand because I have a old Zoom version. My question is, what are the thermal property of the regolith? So you assume a fine regolith on the surface for thermal modeling? I haven't read the paper, admittedly, in Icarus. I apologize for that.
Oh, no, that's fine. We actually tried a variety. We basically tried all, like a low thermal inertia, a moderate thermal inertia, and a high thermal inertia. And they all find actually very similar results.
Thank you.
So,
it's very interesting.
Yeah, thanks.
What variation in your model assumptions that could increase Trojan family small bodies into the NEO population?
So we actually didn't look at the Trojans at all. So because we were focused on the Themis family, so the assumption would just be that we would, add the Trojans into these integrations. We're actually running a larger set of integrations of the whole main belt right now because there's some interest in seeing where else asteroids might come that might infiltrate the comet population. So again, this doesn't include Trojans, but we could certainly do, another set of integrations that include Trojans. But right now, it's just something we didn't look at. Oh, yeah.
Thanks. Are there?
Oh, sorry. Oh, sorry. I see another message. I guess this is Diane. It might have been a typo. So the assumptions for increasing the Themis family small bodies is using non-gravitational forces and also changes in the size distribution that could increase the number of objects reaching cometary orbits.
Henry, it also looks like you have another question from Chris Bennett. He is asking either you or maybe if Norbert's online, if you could talk a little bit about the ice stability modeling that seems to indicate the ice is only stable at depth. And he was wanting to know, have you done this modeling on Themis 24? And does the modeling predict that ice would be at depth there? Or does this agree with the fact that water ice was observed at the surface?
So I think Norbert is online. So if he is, I'd like to pass it to him, but I can try to answer if he's not
online.
Okay, great.
Yeah, so for Themis and the whole outer belt, there is no long-term stability on the surface, right? Only in a subsurface. And but you know, one kind of impacts and recent impacts which can create surface ice. But a long-term surface ice is not stable in the entire asteroid belt, only in the subsurface, in parts of the asteroid belt.